Okay, we are at section 7.7, conservative and non-conservative forces. So let's go to the uh, PowerPoint slides. And if you look here, there's a physics book um, sliding to the right. Now this is after you've already given it an initial push. There's no spring pushing it. There's no hand pushing it. You just push it, have given it an initial velocity and have released it. And it slides and so it has some initial velocity, v sub I, and it travels delta x, and by the time it's finished, it's v equals 0. What slows it down? Well, what slows it down is the force of kinetic friction, as indicated by the blue arrow in the opposite direction of the velocity. So if it, remember, potential energy is the energy of position, kinetic energy is the energy of motion, and we'll see that. So initially, it's 100% kinetic energy. The total energy is the same as the kinetic energy, but now we see a new bar graph, the green one, internal energy, and it's the internal energy of the book. The book has kinetic energy. It's 1/2 times the mass of the book times the velocity of the book squared. So as it slides across the internal energy of the book, at least the cover that's doing the sliding, it's increasing. It's getting warmer. The internal energy has to do with the molecules. The book at a certain temperature, the molecules are moving, but not very, very fast. When it slides, you heat them up. That means the molecules are going faster. We'll learn a little more about that when we get to thermodynamics. But you can see that as the book slows down, the kinetic energy, as indicated by the blue bar, is decreasing, and the internal energy is increasing until all of the internal, once it stops, it's all turned into internal energy. But notice that throughout the sliding, the total energy has not changed. So we have examples of conservative and non-conservative forces. The friction that we look at here is a non-conservative force. So gravitational force, something like gravitational force, that is a conservative force. The friction force is non-conservative. And basically it has to do with the path. Let's look at this. A conservative force, work done by a conservative force on a particle moving between any 2 points, is independent of the path taken by the particle. In other words, if I have a box here and lower it, it's got potential energy when it's up here, and it's got 0 potential energy down here. If it goes down a ramp, it's got potential energy here, and as it slides down the ramp, it's got 0 potential energy. If it were to go down stepwise, it would be the same change in potential energy. So the path that it goes doesn't matter. Work done by a conservative force on a particle moving through any closed path is 0. In other words, as much energy as it takes to raise a book or a box up, it'll take the same energy to bring it down. Those are conservative forces. Now, so those 2 points, the path is in the independent path doesn't change the energy, or the work done on a closed path is not 0, then you have non-conservative forces. So the gravitational work is equal to minus mgj y, dotted with y, so it's the mg y initial minus mg y final, and it doesn't matter what the x is, because as we saw earlier, the j dotted with uh, the I vector will equal 0. So it doesn't matter with the x. It only matters with the y. So it doesn't matter really the path. The only thing that matters here is just the delta y. Uh, the uh, the work from a spring is equal to 1/2 kx I initial squared minus 1/2 kx final squared. And there, the path doesn't matter either. This is also a conservative system. Now, non-conservative forces. The work done by the agent on the book energy system is just mg y final minus mg y initial. So this on the left is a conservative uh, force. On the right, the force of friction is a non-conservative force. And the total mechanical energy is a combination of the kinetic energy and the potential energy. Now let's look at, for non-conservative forces, if you were to slide the book from A to B along the blue path, you would get one increase in internal energy. If you were to do it in the path of A, the brown path, it would be a lot more because you're in contact with more of the surface, and the internal energy increase would be greater. So the path does matter here on this non-conservative forces. And we'll stop there and go on with section 7.8, relationship between conservative forces and potential energy.